Hello everyone. In this lecture, we will discuss about Poisson's ratio of bituminous materials. This is the outline of this lecture. We will see what is Poisson's ratio for elastic materials, then Poisson's ratio for viscoelastic materials. The viscoelastic Poisson's ratio in different modalities of testing such as stress relaxation, creep and recovery, dynamic tension, etc. And then we will see the measurement of a complex modulus and a complex Poisson's ratio. And finally, the conclusions. So what we see here is a typical cross-section of a pavement structure taken from IRC 37. We know that it has different layers such as the subgrade, the granular layers, bituminous layers, etc. For the design, first we need to do the stress strain analysis of the pavement structure, for which we consider the layers or the system to be a layered elastic system, and the material parameters that are considered for the various materials such as granular and bituminous is the resilient modulus and the Poisson's ratio. So in the layered elastic analysis, we have chosen a constant Poisson's ratio for the granular layer as well as the bituminous layer. And the measurement of this Poisson's ratio we have discussed when we discussed our resilient modulus test for bituminous mixtures. Okay. Now, we know that this bituminous mixture is viscoelastic in nature. So, for a viscoelastic material, all the quantities are time or rate dependent. So, obviously, we can expect that the Poisson's ratio will also be a time or a frequency dependent parameter. So in this lecture, we will see how to measure this Poisson's ratio for bituminous materials under creep and recovery test, then stress relaxation test, and also a test in the frequency domain. So it is not straightforward to compute this Poisson's ratio from these tests. So essentially what is done is knowing the elastic solutions for various quantities or parameters, that will be transposed to a viscoelastic solution using a simple tool called correspondence principle. So before going into the Poisson's ratio of viscoelastic materials, let's quickly see what is the Poisson's ratio for an elastic material and what are the various relations connecting the different elastic constants. So for an idealized, purely elastic, homogeneous, isotropic, and a compressible material, Poisson's ratio is defined as the ratio of the lateral contraction to the elongation when it is subjected to a very small uniaxial extension. So as you can see here, this green color box, when you apply a uniaxial tension to this material, it elongates with a contraction in the two lateral dimensions. Here the longitudinal direction is given as x and the other two directions is marked as z and y. Then Poisson's ratio nu is minus the strain in the y direction to the strain in the x direction, or it's also same as the strain in the z direction to the strain in the x direction. So, or the lateral strain to the longitudinal strain. Why we give a negative sign is that when there is an elongation in the longitudinal direction, there will definitely going to be a contraction in the lateral direction. So that is why a negative sign is provided. Now, why do we normally go for measuring this Poisson's ratio? Because as far as the material is concerned, we will be interested in finding its various constants such as the shear property, the modulus, and also the bulk properties. So it is very easy to infer the bulk properties or the bulk modulus knowing the shear or the Young's modulus and the Poisson's ratio rather than measuring the bulk properties for a material. So that is why normally we measure Poisson's ratio. But if you want to infer this bulk properties of the material or the bulk modulus of the material from the shear modulus or Young's modulus and Poisson's ratio, it is very essential that a high precision data is collected as far as the Poisson's ratio is concerned. So we have various constants for an elastic material, and these are called the fundamental elastic constants. So the size, the change in size is expressed in terms of the bulk modulus, which is denoted as K. The change in shape is represented by the shear modulus, which is denoted as G. And you have the reciprocals of these, that the reciprocal of bulk modulus is denoted as the bulk compliance B, and the reciprocal of the shear modulus 1 by G is called the shear compliance G. Now, there are other moduli which are derived from these basic moduli values. For example, suppose the material is subjected to a uniaxial stress with no strains permitted, or the strain is constrained in two lateral direction and there is strain only in the longitudinal direction, then the modulus is called the longitudinal bulk modulus M, defined as the stress by the longitudinal strain. And also the longitudinal bulk modulus is connected to the shear modulus and the bulk modulus by the relation M is equal to K plus 4 by 3G. Now, suppose we apply a longitudinal stress with strains in all three directions possible, whereas the stress in the other two directions is 0, then the modulus is defined by sigma 1 by epsilon 1, that is the stress in the longitudinal direction to the strain in the same direction is called the Young's modulus, or it's also called the tensile modulus or the stretch modulus. And we have a relation that Young's modulus is equal to 9 kg by 3k plus g. Now, also there are compliances defined for the stretch or the elastic modulus, as the elastic compliance D is equal to 1 by E, which again is connected to the shear compliance and the bulk compliance by the relation D is equal to 1 by 3J plus 1 by 9B. Now, Poisson's ratio is defined as a lateral contraction ratio, and it's normally defined as mu. So as we can see here in that same box, as I mentioned, mu is given by minus of epsilon 2 by epsilon 1, or it's also given as minus of epsilon 3 by epsilon 1, where 1 is the direction in which the stress is applied, or it's called the longitudinal direction. Then the other two directions, 2 and 3, are called the lateral directions. Now we have certain relations connecting this Poisson's ratio to the other elastic constants. As we can see here, mu is equal to 3k minus 2g by 6k plus 2g, or in terms of the compliances, it is 3j minus 2b by 6j plus 2b. And also mu is defined as half minus e by 6k, or it's half minus b by 6d. And also there is other relation, mu is equal to e by 2g, or it's j by 2d minus 1. Now, the one relation that we will be interested in further when we are looking at the viscoelastic Poisson's ratio is Poisson's ratio is equal to half minus E by 6K. Further, we have other relations connecting E, mu, K, and G, that the bulk modulus K is equal to E by 3 into 1 minus 2 mu, and the shear modulus G is equal to E by 2 into 1 plus mu. Now, we can see that as the bulk modulus K approaches to infinity, or the bulk compliance B approaches to 0, mu takes the value, the Poisson's ratio takes the value of 0.5. And for any isotropic material, the range of Poisson's ratio is minus 1 to 0.5. Now, let's see what is the Poisson's ratio for a viscoelastic material. So, as we have already mentioned, for a viscoelastic material like bituminous mixture, the Poisson's ratio will be time dependent if you are testing in the time domain, or it will be a complex frequency dependent quantity if the testing is done in the frequency domain. Now, the viscoelastic Poisson's ratio has different time dependence for different test modalities. So this is what we are going to explore in this lecture. Now, how do we arrive at this viscoelastic Poisson's ratio is using a principle called the correspondence principle, which is applied to the longitudinal and the transverse strain in a uniaxial tension. Okay. Now, what is done is that you use a solution to an elasticity problem to obtain the solution to the corresponding viscoelasticity problem, which is having the same geometry and the boundary conditions. You apply Laplace transform on the physical quantity and the material property in the elastic regime, or in the elastic mode, and then apply the inverse Laplace transform for the solution in the viscoelastic regime, or for the time-dependent behavior of the viscoelastic material. So this is the whole idea. You use the correspondence principle and apply the Laplace transforms, and then apply the inverse Laplace transform to convert it to the viscoelastic solution from an elastic solution. So let us consider the first type of test, which is a stress relaxation test, and see how the Poisson's ratio is arrived at. So in this lecture, I will not be discussing about the derivation of this correspondence principle. I will show you how the principle is used to arrive at the Poisson's ratio. Okay. Now, so in this stress relaxation experiment, let us consider that a uniaxial tension is applied in an elastic bar having an elastic modulus of E. Okay. Now, the strain in the longitudinal direction is given by sigma L by E, where sigma L is the stress applied and E is the Young's modulus of elasticity. Okay. Now, the transverse strain, as we know, is epsilon. It is noted here as epsilon TR, is minus nu into epsilon L, or when substituting, you get minus 2 sigma L by E. Now, this is for the elastic material, and also we have seen that for an isotropic elastic solid, we have the relation nu is equal to, now instead of nu, I am using the term nu here. Okay, so nu is equal to half minus E by 6 B, that's equal to half minus 1 by 6 kappa E. Now please note one thing here, instead of K for bulk modulus, I'm using the term B for bulk modulus so that the complaints can be written in as kappa. So in order to avoid the confusion between K and kappa, so B will be used for bulk modulus hereafter and kappa will be used for the bulk complaints. So this relation we have already seen that the Poisson's ratio is equal to half minus the Young's modulus by 6 times the bulk modulus. Okay. Now, the transverse strain, you can get the transverse strain as equal to minus half minus 1 by 6 kappa E into epsilon L. Now, let us consider two cases. The first case is that the kappa is taken as a constant. That is, the bulk compliance is assumed to be constant in time. Say for certain polymers, it could be so. So, let us assume that the bulk compliance is constant in time. Now, first we apply the correspondence principle. So in correspondence principle, we will take the Laplace transform of these parameters. So this is written as epsilon TRP, that is the Laplace transform, is equal to minus half minus 1 by 6. Kappa is taken as a constant and PEP is the Laplace for E and epsilon LP is Laplace for this longitudinal strain. Now, transforming back to the time domain via the convolution theorem and making use of a derivative theorem of the Laplace transform, for a viscoelastic material, we can get epsilon PR T, that is, it's a time-dependent transverse strain is equal to minus half into the time-dependent longitudinal strain plus 1 by 6 kappa integral 0 to T E T minus tau into d epsilon L tau by d tau into d tau. So this is the relation that we get for the transverse strain when you apply the Laplace transforms and the correspondence principle and then convert it back to the time domain. So your transverse strain is now expressed in a time domain. Now, in stress relaxation, we know that we are applying a constant strain, which is defined by epsilon LT is equal to epsilon 0 HT, whereas HT is called the Heaviside step function of time, T, because this epsilon 0 is a strain amplitude. Now, in order to apply it at an infinitesimal small time after 0, that is why you multiply it with a Heaviside step function. So, epsilon 0 HT is the strain that is being applied in the stress relaxation experiment. Now, you can get the Poisson's ratio in relaxation. It is denoted as mu RT is equal to the transverse strain in time domain divided by the strain that is applied, which is epsilon 0. So you'll get the expression as half minus 1 by 6 kappa ET. So this is the strain that we, this is the Poisson's ratio that we have obtained from the stress relaxation experiment. That is why it is denoted as mu R and is a function of time. So here, as I said, the bulk compliance is assumed to be constant. Now, what we can see from this expression is that the time dependence of this Poisson's ratio is less compared to the time dependence of the other material parameter here, which is ET, which is again a time dependent parameter. Now, moving on, Let us consider the second case wherein a bulk relaxation is allowed. That is, you are not assuming kappa to be a constant. Now, again, in the original equation for epsilon TR, let us apply the correspondence principle. So that is epsilon TR P is equal to minus half minus 1 by 6 P kappa P, because the Laplace is applied for the bulk compliance also, P E P and epsilon LP. So that is where the Laplace is applied. And now applying the inverse convolution theorem and deducing the equation, we will get the transverse strain as a time function of time is equal to minus half into the longitudinal strain, which is again a function of time, plus 1 by 6 integral 0 to t kappa t minus tau into integral 0 to t e t minus eta d square epsilon L eta by d eta square into d eta d tau. So what we see is that this involves a nested convolution. Now substituting for epsilon LT is equal to epsilon 0 HT. So, and calculating the Poisson's ratio as minus of the transverse strain divided by the longitudinal strain, you get the expression as half minus 1 by 6 integral 0 to t k t minus tau d e t tau by d tau into d tau. So this is the Poisson's ratio in relaxation, which is a function of time. Now what you see is that this again is a nested convolution which requires several numerical evaluation, and it is a time consuming process. Now let's move to the next test modality, which is a creep and recovery test. So let us assume that the material is subjected to a uniaxial creep in uniaxial tension, whereas the applied stress is sigma LT, which is given by sigma 0 HT. Again, HT is the Heaviside step function, and sigma 0 is the stress magnitude that we have applied. Then the strain in the longitudinal direction, which again is a function of time, is given as sigma 0 JET, where JET is a creep compliance for the axial deformation. Now we have the expression for epsilon TR in the transformation state, in the Laplace transform state as given by this expression. Now substituting the Laplace transform for epsilon T, epsilon LT, that is this longitudinal strain, you take the Laplace transform and substitute here, then the expression becomes epsilon TRP is equal to minus half of epsilon LP plus 1 by 6 kappa sigma 0 P at EP and P JEP, whereas again this is the first case where the kappa is considered to be a constant, that is the bulk compliance is considered to be a constant. Now it is a common well-known rule in viscoelasticity theory that P square EP JEP is equal to 1. Now substituting 1 here and applying the correspondence principle and the inverse Laplace transform, your transverse strain becomes minus half epsilon LT plus 1 by 6 kappa sigma 0 HT. So this is the relation that you get after converting it to the time domain. Now again, you can compute the Poisson's ratio as negative epsilon TR by epsilon L. So in substituting for epsilon TR in this relation, we get mu CT is equal to half minus 1 by 6 kappa 1 by JET. Now this is called mu C. It is denoted as mu C because this is the Poisson's ratio that is estimated from the creep and recovery test. So this is the relation for the Poisson's ratio in creep. Now what you have already seen is that the Poisson's ratio in relaxation, which is given by the equation half minus 1 by 6 kappa ET, and now we have seen the Poisson's ratio in creep as half minus 1 by 6 kappa 1 by JET. From this we can note that the Poisson's ratio in creep and Poisson's ratio in stress relaxation are not the same because here ET and 1 by JET are not the same. It is not, that is, the creep compliance is not the reciprocal of the modulus, Young's modulus. Okay. Now we can see a relationship between this relaxation Poisson's ratio and the creep Poisson's ratio as given by The creep Poisson's ratio is equal to relaxation Poisson's ratio plus half kappa ET into 1 minus 1 by ET JET. Now, this again is for a constant bulk compliance. Now, we have seen that VCT, nu CT and nu RT, they are increasing functions of time, but experimentally it is seen that this need not be true. And also this term ET and JET, this product is less than or equal to 1. We can see that the creep Poisson's ratio is less than the relaxation Poisson ratio. But it is shown from experimental studies that this difference between the creep Poisson's ratio and the relaxation Poisson's ratio is very small. Now let's move to the third test type, which is a dynamic behavior intention, or it's a dynamic test, or the frequency, or the test in the frequency domain. Let us assume that a longitudinal strain is applied of a sinusoidal form given by the expression epsilon L is equal to epsilon L0 sine omega t, where omega is the angular frequency expressed in radians per second. So you are applying a sinusoidal wave form in the longitudinal direction. Now, in dynamic loading, the quantities, whatever quantities are there, are complex in nature, which will have a real part and an imaginary part. Okay? Now, the imaginary part is associated with the phase shift or the phase angle and the energy dissipation. Now, as we already mentioned, the solution in the viscoelastic problem will be obtained by the corresponding solution in the elasticity problem. So in the case of a dynamic test, again, the solution in the viscoelastic problem can be obtained by the dynamic correspondence principle from the corresponding viscoelasticity problem. But in this case, you don't have to do any inverse Laplace transform, because the complex moduli that you substitute in place of the elastic moduli will have a direct physical interpretation. We will see what is that. Okay. So here we can see the applying the dynamic correspondence principle to the expression for epsilon TR. It's minus half into minus 1 by 6 kappa E star epsilon L. That is, we have straight away substituted E star in place of E. And the complex Poisson's ratio nu star is given by minus epsilon TR by epsilon L. And with constant kappa and substituting in the above equation, you get nu star is equal to half minus 1 by 6 kappa E star. Now, again, using the dynamic correspondence principle, suppose you assume that kappa, that the bulk compliance is not a constant, then the nu star becomes half minus 1 by 6 kappa star E star. So this relation that you get for a dynamic testing is algebraic in nature with a bulk property and a tensile property. So it is computationally simple to get this expression from a dynamic testing. Whereas in the case of a time domain testing, as in the case of a creep test or in the stress relaxation test, we have seen that there is a nested convolution integration is needed. Okay. So let us see one experimental measurement of this complex Poisson's ratio in a dynamic loading test. So here you can see that there is a cylindrical specimen which is isotropic and linear viscoelastic material with linear viscoelastic material. And let this be subjected to a sinusoidal axial loading in the direction 1. So these are the three directions 1, 2, and 3. So in the longitudinal direction 1, it is subjected to a stress function of sigma 1 t is equal to sigma 01 sine omega t plus phi 1. And we have the two directions. We have the strain in the same direction given by epsilon 1 t, and the strain in the other two directions, or the diametral directions, or the other two axes, are given by epsilon 2 t and epsilon 3 t. Okay. Now this you can see here the strain in the transverse direction epsilon 2 t is taken as the reference here. So this is the first. So this dotted line, that is the small dotted line, the axial strain. The axial strain in the first direction is taken as the reference here. We can see this is the large dotted line here, which is given by epsilon 1 t is equal to epsilon 01 sine omega t. And with respect to that, the stress in the axial direction is given by This is this black line, which indicates the axial stress, which is sigma 01 sine omega t plus phi 1, where phi 1 is the phase angle with respect to the reference strain that we have considered. And the strain in the other direction, which is epsilon 2 t, which is given by the small dotted line, that is equal to epsilon 02 sine omega t plus phi 2, where phi 2 is the phase angle with the axial strain in the first direction. So as I've noted here, sigma 1t not equal to 0, whereas the stress in the other two directions are taken as 0. Now the strain fields can be explained. So here the strain fields are explained in terms of the time domain. Now we can explain it in terms of complex exponential. As you see here, sigma 1 star omega is equal to sigma 01 exponential j omega t plus phi 1. And epsilon 1 star omega is given by epsilon 01 exponential j omega t. And epsilon 2 star omega is equal to epsilon 02 exponential j omega t plus phi 2. As I mentioned, epsilon 1, the direction of epsilon 1 is taken as reference, and the other two, the stress in the longitudinal direction and the transverse strain in the other direction, has a phase angle of phi 1 and phi 2, so which indicates the time shifts of sigma 1 and epsilon 2 t with respect to epsilon 1 t. Now phi 1 can be expressed in terms of the time difference as omega delta ti also, if phi I is equal to omega delta ti, where j is the imaginary unit and omega is the angular frequency. Now in this test with sigma 1 t, we can obtain the modulus, Young's modulus, or the complex Young's modulus, as given by E star omega is equal to sigma 1 star omega by epsilon 1 star omega. Now substituting for these two functions, we get the complex Young's modulus as sigma 01 by epsilon 01 exponential j phi e, where phi e denote the phase angle of E star omega. As we can see from this figure, E star has a phase angle of phi e, which is equal to phi 1 itself, which is in the direction of sigma 1, sigma 1 star. And the complex Poisson's ratio nu star omega is given by the expression minus epsilon 2 star omega by epsilon 1 star omega, which is same as the transverse strain by the longitudinal strain. Now substituting, we get epsilon 02 by epsilon 01 exponential j phi nu, where phi nu is the phase angle for the Poisson's ratio. As you can see from this figure, x-axis denote the real part and y-axis denote the imaginary part. Your nu makes an angle of phi nu with the real part, which is given by phi 2 minus pi. So this is the phase lag for the Poisson's ratio, and phi e is the phase lag for E star. Okay. Now we can take the mode of the Young's modulus and the Poisson's ratio as given by mode of E star is equal to E0, which is sigma 01 by epsilon 01, and the mode, or it's also called the norm of Poisson's ratio, which is equal to nu 0, which is epsilon 02 by epsilon 01. Now also we can express this complex Young's modulus and complex Poisson's ratio in terms of its real part and imaginary part as given by E star omega is equal to E1 omega plus j E2 omega, where E1 represents the real part and E2 represents the imaginary part. Similarly, for the Poisson's ratio, the complex Poisson's ratio, you have nu 1 omega plus j nu 2 omega, where nu 1 omega represents the real part and nu 2 omega represents the imaginary part. So from this test experiment, when the material is subjected to a complex sinusoidal loading in the longitudinal direction, we can make these measurements, and then from the strain measurements, you can compute the complex modulus and the complex Poisson's ratio. So for the test protocol, it is essentially the measurement of E star and nu star simultaneously. So it is necessary that you take measurements or the strain measurements in the transverse, in the diametral dimensions, or it's in the longitudinal direction, as well as in the two transverse directions, or it can be the diametral or the circumferential direction in order to calculate the nu star. Okay. Now, as you can see here, in this case, there is a transverse strain gauge as well as an axial strain gauge. Now, normally these measurements are made in an experimental setup at the mid height of the specimen. Now, the loading that we have applied, it can be a sinusoidal loading or it can be a Haversine loading. And the test can be conducted either in the stress control mode or it can be in the strain control mode. Now, first of all, you have to apply 2 or 3 cycles so that you attain a steady state. And thereafter, you can have 2 or 3 cycles of load cycles and take the average measurement. But it should not be too many of cycles that other aspects such as the temperature increase all will creep in the measurements. So the number of test cycles and the number of initial cycles are to be chosen for material to material. It may change, so it has to be chosen appropriately. Now, what is very important is that, see, this Poisson's ratio is viscoelastic property. The Poisson's measurement of the Poisson's ratio will directly depend upon the phase lag. Okay, so it is very important that these longitudinal measurements or the transverse and the longitudinal measurements are made simultaneously without any time lag and with high precision, that this change of phase lag is captured effectively or without any error. So this is how the experiment is being carried out, and you can measure the E star and mu star values from the expressions that we have mentioned here. Now, this is one study by Graziani et al. In 2017. We can see that from the Poisson's ratio and the dynamic modulus measurements that is conducted at different labs, they have plotted a cold diagram and a black diagram for the complex Poisson's ratio. We can have an idea about how this varies. We can see here this first figure is a black diagram. The black diagram is the one which is plotted with the norm value and the phase angle value of the complex Poisson's ratio. So it is norm mu 0, and this is the phase angle phi nu of the Poisson's ratio plotted here. And also this is a second figure, which is called the cold diagram, which is a plot between the imaginary part and the real part of the Poisson's ratio. Okay. And also there is a master curve is fitted for the complex Poisson's ratio. Again, master curve is with a reduced frequency at one reference temperature. You can see that this is a master curve plotted for the norm of the Poisson's ratio, and this is the master curve plotted for the phase angle of the complex Poisson's ratio. So what we can see is that this master curve is not monotonic in nature. It has an increasing as well as decreasing nature. So the complex Poisson's ratio need not be monotonic in nature. And also the master curve of this phase angle shows that there can be a change in sign as well. So coming to the conclusion, the analysis of flexible pavements needs a realistic estimate of the material parameters. And we know that this bituminous mixtures which are used at the top layers of the pavement structure are viscoelastic in nature, and hence the Poisson's ratio for the same also will be a time or a frequency dependent parameter. And this viscoelastic Poisson's ratio will have different time dependence depending upon the test modality that we have chosen. We have discussed in this lecture different tests such as dynamic testing, in a frequency domain, and the second one was a stress relaxation test, and the third is a creep and recovery test. So one was in the frequency domain and the other two were in the time domain. So we have seen that in all these domains, the viscoelastic Poisson's ratio will have a different time dependence. So, but we have also seen that the Poisson's ratio in creep and in relaxation will have only a minor difference unless there is a large relaxation strength difference. Okay. And also this Poisson's ratio, it need not increase with time and it need not be monotonic with time also. So when we do an analysis of a flexible pavement structure, it is necessary that we consider this viscoelastic nature of the bituminous layer with a viscoelastic Poisson's ratio and a viscoelastic modulus, which we call it as a surrogate modulus. So the use of this and the analysis of a pavement structure and design, etc., will be dealt with in another course. So with that, let me conclude. Thank you. So these are some of the references which are used for the preparation of this lecture. So you can have a further a look at these references if you need any further information on how these equations are derived or how the correspondence principle is derived. You can have a look at these references. Thank you.